Hello friends, welcome to Tech-fundas Tech YouTube channel. So today we'll be starting with the fundamentals of digital circuits. Welcome back. Let us revise on the basis of what do you mean by basic gates, what do you mean by Boolean laws. So what are the elements of digital logic? So the logic refers to the something which can be reasoned out. That means whatever may be the example is given to you, or if the input is given to you and what is the output, if there is a correlation between input and output, and if how the output is derived, if we can express it in terms of something called as a logic, we can refer it as a logic. In terms of digital logic, we refer it as a Boolean logic. So the several logic statements, when it is combined in the form of logic functions, so these logic functions can be formulated mathematically, called as a Boolean algebra. So Boolean algebra is nothing but it's a mathematical representation of logic. So where we can express the function in terms of logical expressions. So the most important parameter is a variable. So the variables are the different symbols in the Boolean expressions. So let us call it as a the variable a, b, c, d, or whatever may be the nomenclature you want to give for expressing your Boolean algebra. The variable can be represented in terms of the names. That names we can refer it as a variable. So there are basically four types of basic gates we can work on, or basic logic elements which we can work on. So basic three gates are NOT gate, AND gate, and OR gate, and a flip flop. Okay. Uh, so let us try to understand what is the functions of the basic digital logic. So many operations can be performed by combining the gates and the flip flops. So there are combinational circuits as well as sequential circuits. What do you mean by combinational circuits and sequential circuit? We'll learn it in upcoming lectures. So keep watching my channel so that you can understand what do you mean by basic combinational circuits and logical circuits. Some of the most important arithmetic operations we can perform with the help of these logical functions, uh, such as arithmetic operations, comparison, code comparison, conversion, encoding, decoding, multiplexing, demultiplexing, shifting, counting, and storing. So these are the some of the few examples that we can perform with the help of combinational circuits as well as sequential circuits. So there are other applications like frequency division and data transmission also. So this is the extended version of, or this is the extended application of the devices called as a multiplexing and demultiplexing. So we always came across the word called as an integrated circuit. So what do you mean by integrated circuit? So integrated circuit is nothing but where we combine the various logic gates together to perform a particular task. So it is integrated in a single circuit, and that is available as a integrated IC, integrated circuit, which is called as a IC, and IC may be again classified into the two types depending on the application. Which type of signal it is performing. So if the IC is using the analog type of signal, then we will call it as a linear ICs or analog ICs, and if the input is to the IC is digital, in the digital form, then on that basis we can call it as a digital ICs. So the ICs used for 7400 series or 74XX series, so that comes under digital ICs, and the linear integrated circuits such as operational amplifiers or PLL type of devices, we can call these ICs as analog ICs or linear ICs. So digital ICs are the collection of resistors, diodes and transistors. So depending on that, again the devices are classified into different logic families. So we will discuss it soon also, but let us try to focus in this lecture on the basic fundamentals of the basic gates. So these ICs are available in dual in-line package, that is DIP package, as well as flat packages. So there are different types of levels of integrations are available depending on the number of gates available per IC. We can classify it in small scale integration, that is SSI type of ICs, which may consist 10 to 12 gates. Then medium scale integration MSI, which consists 12 to 99 type 99 gates on a single chips. So the decoders, counters, resistors, multiplexers are the examples of this MSI type of circuit. Then the large scale integration, which consists of near about 100 to 9999 gates per chip. So small memories and small microprocessors fall into this category, and very small large scale integration where the 10,000 to 99,999 or more than that, we call it as a VLSI. And apart from that, there are ULSI type of devices are also available where the complexity is more. So the chips nowadays are used in these categories, VLSIs and ULSIs. So the basic first fundamental gate is OR gate. So this is the symbol of OR gate, which consists the two inputs. So here we will be considering the two input OR gate. There might be a different type of inputs are also available. 4 input OR gate will be also available, but our basic focus will be on the basic fundamental of the gate, that is the two input OR gate. So what this OR gate represents? So here we can see that. So OR is the logic. That means either this input or that input, either input A is available or either input B is available, you will be getting as a output Y equal to 1. So if you want the output Y equal to 1, then in that case either we want this output should be either equal to 1 or this should be equal to 1. Then and then only output Y will be 1. So it can be represented in the format of the Boolean equation Y is equal to A plus B. So this plus is a logical OR operation. This is not a mathematical plus operation. This is a logical OR operation, A or B, right? So this is the truth table for A or B. So here you can see that when input A is 0, this is 0, right? And input B is also 0, so your output is also 0. Your output is also 0, right? So here when input A is 0 and input A is 1, here you can see that input A is 1, your output A is also 1. That means either of the input is present as a 1 or both of the inputs are present as a 1, your output is 1. So this is either or, this or this. You can see that this B is 1 or A is equal to 1. So here we can see that, the output is equal to 1. So this output is equal to 1, right? So we can represent it with the help of electrical circuit also. Now the switch S1 and switch S2 are connected in parallel to each other. Now see, this battery is connected to this circuit. Let us consider it as a bulb. So when S1 is on, the circuit gets completed, right? When S2 is also on, the circuit gets completed, or when both are on, the circuit gets completed, the current flows through the circuit. That's why the parallel combination we will call it as A or B. So let us take an example that whenever you are passing through one of the, let us say when you are traveling on the road, and when you have two options, either this or this. So when the traffic on road A is a big one, that you may consider it, there is a blockage on S1 path. So you can choose the S2 path and you can complete the loop, right? So A or B, so S1 is available, path S1 is available to you, or path S2 is also available to you. So this is what that means, you can complete your loop. That's why it is called as a LOR logic, and you can come up with this one. So here it is the example of this one. So you can see that when B is switched on, the light is bulbed. When A is switched on, the light is turned on. See, here it is the example of the same one. So A is on, light is on. When B is on, light is on, or when both are on, light is also on. So this is what the example of OR gate. Now I'll move to the next gate, AND gate. So this is the symbol of AND gate. So AND gate, the output is 1 when both when both inputs are 1. So either OR is not applicable. Here A and B should be available. This is what, and it is represented by the example called as a dot. So it is multiplication type of, right? It is a multiplication type of application. A and B. So it is represented as A dot B, or many times you can write it simply A B. That is also applicable. So y is equal to AB means it is a product of two variables. So it indicates a AND operation, logical AND operation. It's not a multiplication, it's a logical AND operation. Okay. So here it is the example of this one. So you can see that when input is 0, A is 0 and B is 0, so your output is also 0, right? So when A is 1, A is 0 and B is 1, right? So 0 dot 1 is output 0. When A is 1 and B is 0, still output is 0. When both are 1, then and then only the output is 1. So this can be again represented with the help of this circuit. So when the switch S1, will be turned on, okay, so S2 is off, so the bulb will not glow, okay, because there will not be current flowing through the circuit. When S1 is off, this is off and this is on, okay. When this is off and this is on, still the path will not be completed because there will not be circuit. When both are on, that means this is also on and this is also on, then in that case the bulb will glow. So let us try to understand with the analogy. See, when both are on, then and then only the circuit will be on, right? So you can see that when both are on, A is on, circuit, when both are on, the circuit is off. A is on, circuit is off. When B is on, the circuit is on. So this is what the example of A and B working. So AND gate works in a series combination. The switches are connected in series. When both are on, then and then only. Okay, so this is how you will be working. Okay, next. Now we'll move to the third function, that is called as a NOT gate. It is an inverter. It inverts the output. So when your input is 0, your output is 1, and where input is 1, your output is 0. So this is how you will be working with. So it is an inverted one. So it is indicated by the function y is equal to A complement. A bar means it is a complement of A. So output gets inverted. So the same example we have discussed. When A is equal to 0, output is equal to 1. When A is equal to 1, output is equal to 0. So if you connect a switch parallel to bulb, the circuit works. Now let us see how it works. So this is VCC, right? So this is VCC, or V you may call it as, or this is switch 1. When it is closed, the current will flow through this circuit. So it will not reach to the bulb because the bulb's resistance is quite higher than this one. So the low resistance part will be this one. That's why the output, the bulb will not glow. So when this is off, so we are talking about the switch A and 1. So A is equal to 0 means this is off. When this is off, this is the path we will be following. So the current flows through the bulb and bulb glows. And when the switch is on, that means A is equal to 1, the current will be there and the circuit gets off. So this is how the circuit works. So here we can see that when the switch is on, the bulb is off. When the switch is off, the bulb is on. So it gets inverted, exactly opposite of the input. Okay. Okay. Now the NAND gate is the universal gate. So this is the representation. So it is a combination of, I may call it as a AND followed by a NOT gate, and followed by a NOT gate. So this is a combination and it can be represented as this one. So a AND gate is represented, and this circle is nothing but and the indication of inversion of the input. So AND followed by a NOT gate is a NAND gate. So output is 1 when at least one of the input is 0. So output is 0, and for all the, when all the output exactly you will be getting the opposite of this one AND gate. So the truth table of AND gate, we know that when A and B and this is Y, so we may call it as a Y bar is the output of NAND gate. When it is 0 0, output of AND gate is 0, so this you will be getting 1. So this is 0, this is 1, output is 0, you will be getting 1. This is 1, output 0, output of AND gate is 1, you will be getting 1. This is 1, this is 1, output you will be getting 1. In this case output is be 0. So output is equal to 1 if at least one of the input is equal to 0. So you can see that at least one of the input is 0. Here in this case you will be getting the output is equal to, and when all the inputs are 1, output is equal to 0. So this is what the representation of A and B. So you can represent it we can represent it as A B bar. This is also, it can be represented as the universal NAND gate. So you can see that. So this is the combination of NAND. So this is the circuit works with a NAND when both circuits are on, when S1 is on and S2 is also on, then and then only the current will flow through this one and the output will not flow. Otherwise this circuit will be broken one and the current flows through the bulb and you will get the output high. So this is how the NAND circuit works. Okay. Then the NOR, again it is a combination, so we may call it as a OR followed by, so this is OR followed by a NOT circuit. Okay. So this is called as a NOR gate, universal gate. So for NOR gate, output is equal to 0 if any of the input is 1, if any of the input is 1, and output is equal to 1. So if all the outputs are 0, so it is represented by A or B complemented, right? So this is what the example is. So when both the outputs are 1, when both the outputs are 0, your output is 1. In other cases, If any of the input is 1, your output is 0. So this is what the combination for NOR circuit. So let us try with this one. When both are 0, that means the current will not flow through the circuit. So this circuit is broken and the current will flow through this one and you will get the output. Now any of the switch is on, then in that case this path is on and there will not be any current through this circuit and the bulb will be off. That's why you will be getting the circuit is equal to on. Now the next important extracted circuit is a XOR gate. So XOR gate, for XOR gate output is equal to 1 if both inputs are different. So if you want to compare in most of the circuits, if you want to compare the two inputs, the XOR gate is generally utilized. A XOR B. So here you can see it is represented by, it is a combination as written as A, this is OR and this is XOR. So XOR combination will be, this is plus surrounded by a circle. So this is the symbol for XOR. Okay. So it is nothing but A B bar plus A bar B. So the circuit is implemented like this, A B bar plus A bar B. Now let us try to work with this one. Let us have a circuit, this is A B. Let us have a bar B and A B bar. Okay, and let us have the output Y, which is an XOR. So when both are 0, this is 1 and this is 0. So this is 0 and this is 0. So your obviously output will be 0. Okay, when this is 1 and this is 0, so A bar B is equal to the combination of A bar B is equal to, excuse me, what is the combination of this one? So this will A bar means complement of this one, and this is 0 and this is 1 because A is 1 and B bar is 1. So this is 0 and this is 1. So ORing of this and this will be 1. Now this is 0 and this is 1. Now in this case this is 1 and this is 0. So the combination of these two will be obviously 1 because this is ORing function, right? This is OR. Now let us consider this is 1 and this is 1. So obviously this will be 0 and this will be 0. So you will be getting output equal to 0. Right? So this is how we will be working out with the XOR gate. So this is the combination of XOR gate. Electrically we can represent with XOR gate. So you work on this one and just try to find it out whether the truth table I have shown over here, according to this whether this circuit will work or not. Okay. So we will stop here. In next lecture we will start with a Boolean laws and Boolean axioms. Thank you.